Okay, hi guys. So in this lecture, we'll be discussing on the degree of dissociation in terms of molar mass or vapor density. So let's get started. So we'll be talking about degree of dissociation in terms of molar mass oblique vapor density. Okay. So let's suppose we have a reaction in which we are converting A gaseous in B gaseous form. So let's say at the initial stage number of moles, and for A would were in A were A, and initially B was having B moles, so moles at equilibrium would be, let's say, degree of dissociation of A was alpha, so 1 minus alpha number of moles would be present for A. And similarly, okay, so let's not complicate the example. Let me start with a simple example. So let's say B was having 0 moles, so, and also A is converting into n number of B's or n moles of B's. So in this case, number of moles of B at equilibrium would be nothing but Na alpha. Okay, so initial moles at equilibrium divided by, or rather I should say that total moles at equilibrium divided by initial moles of reactant. The ratio would be nothing but A1 minus alpha plus Na alpha divided by A. So this is total moles divided by at equilibrium divided by initial moles, which I am denoting by M naught or MO, whatever you may want to call it. So MT by MO, the ratio would be 1 minus alpha plus N alpha, or you can write it as 1 plus N minus 1 alpha. Okay, so from here, let's suppose we know MT by MO, and we want to know, and we want to express MT and MO as a function of, or rather we want to find the value of, or equate, or better get the value of alpha in terms of MT and MO. So what we'll be doing, so N minus alpha would be equals to MT minus MO divided by MO, and from here we can get the value of alpha as MT minus MO divided by N minus 1 MO. Where MT is, I am again reiterating that MT is molar mass of reactants okay. So before that, let me write one more thing here, is that, so let us actually more simplify this value. So we know that MT is we defined as moles of, or other total moles of mixture. Okay, and MO we defined it as initial moles of reactants, and we can further write number of moles as we can write MT as weight of the mixture at equilibrium divided by molar mass of total mixture, and I can write MO as weight of rather initial weight of reactant divided by molar mass of reactant. I'm writing that as MO, small mo. So here if we look more carefully at this reaction, then we can see that due to the law of conservation of mass, we can say that whatever initial mass was present in the solution, or whatever initial mass of A was present at equilibrium, also the mass of the total mixture would also remain the same. At equilibrium, some of the moles of A are present and some moles of B are present, but still the total overall mass of the mixture would still be equal to the initial mass of the reactant or A. So we'll be using this fact and equating WO with WT, or rather W mixture you can write it as WT, and W reactant you can write it as WO. So since WO are same, we can write that MT is equals to, rather MT by MO is equal to small mo by small mt. Okay, so just applying the same here as well. From here we can write that capital MT is small mo upon or rather we can put it in the initial equation as well. So just putting it there, we can see that if you put it here only, we can see that MT by MO would be nothing but, so this is nothing but n minus just deriving the further equation from here, we can write n minus alpha as MT by MO minus 1. So MT by MO is nothing but MO by MT. So n minus 1 alpha would be MO by MT minus 1. So now equating alpha, we will get MO minus MT divided by n minus 1 MT. Where obviously please remember the fact that MO is molar mass of the reactant or initial molar mass of the reactant, and MT is nothing but molar mass of mixture at equilibrium. Okay, so next let's see one more example. So suppose we have a reaction that PCl5 gets disintegrated into PCl3, which is this solid, and Cl2, which is gaseous. So in this case, MO or the initial mass would be molar mass of PCl5, and MT would be nothing but molar mass of mixture. Molar mass of mixture. Oops, again the same mistake. Molar mass of mixture. Yes. Which contains obviously PCl5, some amounts of PCl3 and some amounts of Cl2. Now let's define one important term, which is called vapor density. So vapor density is defined as, mathematically we can write vapor density as molar mass divided by 2. Okay, so this is the term which we use for vapor density, and as we know that alpha is equals to MO minus MT divided by 2 divided by n minus 1 rather, n minus 1 into m t, obviously where mo is again the molar mass of reactant and mt is the molar mass of mixture. Okay, now we can write vapor density as dt or do, which would be equal to mo by 2 and mt by 2. So this is I wrote both in a separate line. Let me write both in a separate line. So dt would be mt by 2. So just replace the value of mo and mt here. So we will be getting again the same equation with respect to vapor density here. So d naught minus dt divided by n minus 1 dt. Okay, so now let's move on to seeing new concept, which is degree of association. By the way, in the example of PCl5 disintegrated into PCl3 and Cl2, n here would be 2, because we saw in the previous or in the hypothetical example we converted Ag into n moles of Bg. So here n represented number of moles of products formed, n here would also represent the number of products formed. So n here in this case would be 2, because two products are formed in this case. Okay, so I hope you can put the value of n minus 1 here. N is 2, so alpha would be du minus dt by dt, or mo minus mt minus mt. Now let's discuss degree of association. Suppose we have n moles of A all combining together to form An. Okay, so initial moles would be A here and 0 here, and final moles at equilibrium would be, we will have A minus alpha A and alpha A by n here. Okay, so we can write that, I'm just continuing from here, that moles at equilibrium rather divided by initial moles of reactants would be A1 minus alpha plus alpha A by n divided by A1 minus alpha. So from here we can write, and we can also equate this to molar mass of, rather let's first associate it with number of moles of total moles at equilibrium, which would be mt, and initial moles of reactants would be mo, and we can write that mt by mo would be nothing but weight of mixture at equilibrium divided by molar mass of mixture divided by weight of reactant, or initial weight of reactant divided by molar mass of reactant. And we know W2 is equals to WOY because of law of conservation of mass, that whatever mass is at the equilibrium of the mixture would have definitely come from the initial mass of reactants. Hence we can equate W2 with WT. So just cancel it out, and we can write it in the form of mo upon mt, or in other words molar mass of reactant divided by molar mass of observed molar mass of mixture. Mt represents the molar mass of mixture. So just equating A1 minus alpha plus alpha n by 2 divided by A would be equals to, Initial moles is A, not A minus alpha. A into 1 minus alpha will not be there, it would only be A. Should be equal to MO upon molar mass of reactant divided by molar mass of mixture. So from here we can calculate alpha as MO minus MT divided by MT 1 upon n minus 1. Okay. So before ending the lecture, I'll also like to give some examples on the same. So suppose we have something like so let me reiterate the formula first, then we'll come to the point which I was, or some examples which I was trying to give. MO minus MT divided by MT 1 upon n minus 1. So here MT is nothing but molar mass of mixture, MO is nothing but initial, rather molar mass of reactant, okay, and alpha is degree of association. I hope you remember that the equation is as follows. So this is degree of this association reaction, not dissociation. So alpha is degree of association here. Okay. So let's look at some example. So suppose we have 2Ag converting it into A2G. So here N would be 2. This is the classic example of dimerization. Okay. And we can also have for N equals to 3 trimerization, and for N equals to 4 it would be tetramerization. So with this we come to the end of this lecture. From the next lecture onwards we'll be discussing on Le Chatelier's principle. So till then, good luck and goodbye.